Morning guys, so we're going to do Forces and Friction, which is chapter 5 from the second year mechanics book. I am going to go through all the examples to the whole of the chapter, hopefully in one video, which means you might have to pause or skip ahead to the bits that you need, pause when you need to and do the exercises, but you'll have all the examples on one video, so it may be a little bit of a long video. Now in terms of forces, just zoom in a little bit, there we go, okay. I've put any little facts that they gave you at the top. So you've got a force applied at an angle direction to the direction of motion. So basically we've done pulling forces where everything is horizontal. So a tow bar that's pulling a car, that's a horizontal action. But in this case we're looking at a force that's pulled on an angle. So what you need to do is you need to split that force into its horizontal and its vertical components. You might also come across it as its perpendicular and parallel components, which we'll do when we get onto angles where you've got an inclined plane and then a force that's pulled at a different angle to the inclined plane as well. So if you look in the book, everything is done using cos of the angle. There's nothing wrong with that. I just feel it's a lot easier if you think back to GCSE, do SOHCAHTOA with your triangle, label your sides opposite, adjacent, hypotenuse, and you end up using either sine or cos. Now, the reason for that is when you stick to everything just being cos, it does mean that you have to do a lot more angle facts, a lot of messing about with what angle you're using, and it just, in my opinion, overcomplicates things. It's much easier if you just do sine and cos, depending on which side you're after. So if I explain that, here's our force F newtons, and we want to split it into its horizontal component and its vertical component, okay, so that we can resolve horizontally and vertically like you've seen before. So all we're going to do is, if this is my angle, I've got opposite, adjacent, I'm going to write the words actually just because it does tend to blend in, and hypotenuse. So if I want the vertical component, I'm on the opposite side. So if I'm looking at opposite and hypotenuse, for those who used SOHCAHTOA like this at GCSE, you'll know that for opposite you do sine of the angle times the hypotenuse. Hypotenuse is F, so if I do sine theta times F, we're just going to get F sine theta as my vertical component. If I then looked instead at this side, I'd have adjacent and hypotenuse. So that's the cat part of SOHCAHTOA, in which case you're doing a cos one. Because you're looking for adjacent, you're doing cos of the angle times the hypotenuse. So you get F cos theta is my horizontal component of my force, okay, which is much easier than messing about with angles to get everything in terms of cos. So if we look at that in terms of some examples, and as always, you know there's something I'm going to miss. So if I've got a 9 Newton force, it's being pulled at an angle of 40 degrees to the horizontal. So all we're going to do is join the end of your force to the horizontal to create our right angled triangle. You're always aiming for a right angled triangle, otherwise SOHCAHTOA is not going to apply. So I know this side is 9 and it's also our hypotenuse. This side's the opposite, this one's the adjacent. So if I'm looking for the vertical component, that's got opposite, so it's the sine part, which means I'm doing 9 sine 40. You will get this as a pattern and eventually won't have to keep writing everything out. And then this one on the bottom is our adjacent side, so it's the cos part, in which case for adjacent, cos of the angle times the hypotenuse, so I'm doing 9 cos 40. Okay, we're actually going to type those in a calculator and give our answer in vector notation form, which is the I and J notation. Now, just as a reminder, I is your horizontal components, J is your vertical. Okay, so 9 sine 40 is going to give us 5.79, and 9 cos 40 is going to be 6.89. Just really quickly, remember we are working in degrees, so just make sure you calculate it in degrees. So to give this force in vector notation, the I format is 6.89. So you've got 6.89 I, remember it is a vector, so underline your I, plus 5.79 J, and it's a force, so it's all in newtons. Just really quickly before I move on, I did mean to say this at the start. Always look at your force to begin with. You can see that my force is travelling in the positive X direction and the positive Y direction, so getting positive answers is absolutely fine. On the next one, you can see that actually if I just draw in my dotted line, the horizontal x direction is negative, the vertical y direction is also negative. So we're actually going to treat it as minus 100. And the reason for that is because otherwise your calculator is going to give you the positive version of everything. We obviously want the negative one. Now you can, if you want, mess about with your angles and find the angle to the vertical and do it all that way. There's nothing wrong with that. That's, I think, how they do it in the book typically. I'm not going to do that. It's just a lot more effort than is necessary. So all I'm doing on this one is I've got this side is the opposite, this side's the adjacent, and the hypotenuse is obviously 100. So if I want the vertical side, I'm doing adjacent, so that's your cos side again. So I've got 100 cos 18, but as I said, your force is acting downwards, so it's minus 100 cos 18. Okay, which if you type into a calculator is going to give us minus 95.1. Okay, if I then look at the horizontal component, it's opposite, so it's a sine one, so it's 100 sine 18. Again, it's acting in the negative direction, so it's minus 100, which saves us messing about with our angles. Chuck that into a calculator, you're going to get minus 30.9, and all we want to do is put that into I and J notation. So I is your horizontal, so we've got minus 30.9 I minus 95.1 J for your vertical, and it is a force, so in newtons. Okay, if I look at the next one then, so this one I might have to zoom out for a little bit. There we go. So if I look at example 3, this time we've got a box of mass 8 kilograms. So remember, that means the force acting downwards is 8g, and you've got a normal reaction force acting upwards. A force of 10 newtons is being applied at an angle of 30 degrees to the horizontal, causing the box to accelerate horizontally across the floor. So acceleration is in that direction. Okay, it means there's no acceleration vertically at all. So if we want to work out the acceleration of the box, we obviously need to resolve our forces in a horizontal direction. Again, stick with your direction of motion. So this is using F equals ma. So you do the resultant of your forces. So we need any forces pulling in the direction we're after are positive, any pulling against are negative. So the only force we've actually got acting horizontally is the horizontal component of the 10 Newton force. So if we do what we did earlier, we've got this side is opposite, this one's adjacent, this one's hypotenuse. Hypotenuse is obviously actually the force, so the hypotenuse is 10. Because we want the horizontal component at the minute, I'm using the adjacent side, so that's your cos part. Okay, so I'm doing cos of the angle times the hypotenuse. So I've got cos 30 times 10, so 10 cos 30. I haven't got any forces acting against us because I've got a smooth horizontal floor. There's no friction involved, and there's no other forces pulling, pushing, acting against in any way. So that is the resultant of all my forces, equals mass times acceleration. Now remember, mass is just the 8 part because it's just 8 kilograms for the mass. Once you times it by g, you've got weight, not mass anymore. So it's 8 times acceleration. So all I'm going to do is divide by 8. I get acceleration equals and you get 5√3/8, and I am going to leave it as that because that's not a very nice number. Okay, but that's it, that's our acceleration. Part B says, can you work out the normal reaction between the box and the floor? So if I want the normal reaction R, I need to resolve vertically, and again, because I'm looking for R, I'm going to resolve upwards. Now you can follow force equals mass times acceleration, that's absolutely fine, but obviously since the object is not accelerating up or down in any direction, it's not being lifted into the air, it's not being pushed through the floor, okay, you've just got the object moving right or left, which means acceleration for up and down is obviously 0. So this side here would just work out as 0. So what you can do instead is just think about it logically. If the object's not moving up or down, the forces that are trying to lift it up have to be equal to the forces that are trying to pull it down, so that it's not moving in either direction. So forces upwards, I've got R is acting perfectly upwards, and then I need the vertical component of my 10 Newton force. So that's on the opposite side. So this is the sine one. So I'm doing sine of the angle times the hypotenuse. So I get 10 sine 30. And that has to be equal to all the forces that are acting downwards, which is just 8G. So I get my resultant force is 8G minus 10 sine 30. Chuck it in a calculator and we get 73.4 newtons. Okay, and that's it. Example 3 done. Right, if we look at example 4, now this one is a little bit more complicated and is actually much better if you redraw the diagram. So just for a second, I'm going to redraw my diagram so that it's in a bit of space. I can edit it. So now remember, when you've got two forces acting, the best way to solve this is using what they call the triangle law. Basically means when you've got two forces, the resultant is if you move one force to the end of the other. Okay, so if I move this force to the end of the other one and then join them up, I create a triangle. That triangle rule helps us solve it. So I'm going to leave Q where it is at an angle of 30 degrees. That's also meant to say Q. Okay, now P originally is at a 45-degree angle there. Okay, and now what I'm going to do is just move P to the end of Q. Okay, and then I've got that angle there was originally 45 degrees. Now the reason for that is I can get my resultant force. Sorry, I just need to turn the paper a second. Right, so this is now force P, and this is my resultant force that we're looking for. So this is the one we're trying to find. Now the reason I did that is because what you've ended up with is a set of parallel lines, and we know from GCSE that if you've got a set of parallel lines, I can use the supplementary rule to tell me that this angle, which in total is 75, plus this angle has to equal 180. So this one must be 105 degrees. Okay, now I know P has a force of 10 newtons and Q has a force of 8 newtons. So all of this mess here actually just ended up being a triangle with an angle there of 105, a side of 10, a side of 8, and a side we're trying to find. So if you've got a triangle with just one missing side, you're looking at the cosine rule. Okay, so just remember, cosine rule is the angle is labelled as A, so this is side A, side B, side C. If you don't know your cosine rule, you do need to learn it. And all we're going to do is chuck in all our values and find out what our resultant force is. So R squared is 10 squared, 8 squared, minus 2 times 10 times 8 times cos of 105. And then just remember to square root your answer. We chuck all of that into a calculator. We're going to get 14.3. So I've got my resultant force, but it does ask us for the direction that that resultant force is acting in. Now, that means we're going to need to find this angle here, okay? Because I need to know what this angle is to give the direction that my force is travelling in. The only way I can do that is if I can find the whole angle in my triangle and then subtract 30. So if I find my whole angle, what you've got is an angle and an opposite side, an angle and an opposite side. So I can now apply the sine rule to this from GCSE. So I'm just going to call this x. So I get sine x over 10 has to equal sine of 105 over, and then try to use the whole number rather than a rounded number. And so all we're going to do is times up by 10 and do sine to the minus 1. So I've got 10 sine 105 over my answer, and if I do sine to the minus 1, I get x equals 42.4 degrees. So I know this whole angle here is 42.4. So if I subtract this 30, that little angle there would just be 12.4 degrees. So when we describe R, it's 14.3 newtons is the resultant force, and the direction is 12.4 degrees above the horizontal. Obviously, if X had came out smaller than 30, it would have been so many degrees below the horizontal. Okay, and that's it. We've got our force and its direction. So that one is a little bit more complicated, but it is just sine and cosine from GCSE. It's just a bit of fiddling about with the diagram in the beginning. Right, and then if we look at example 5, which is our last example for this first section, you've got 3 forces acting on a particle as shown. Given that the particle is in equilibrium, calculate the magnitude of P. Equilibrium means that it's not moving anywhere, so any forces acting upwards have to equal the forces acting downwards. Any forces pulling to the right have to equal the forces pulling to the left, because your object's not moving in any direction. Okay, think hanging a picture frame. Okay, everything's in perfect equal motion, picture frame's not moving off the wall. So all we're going to do is each one of our forces we're going to split into its horizontal and its vertical components. So each time we're creating that right angle with our horizontal line. Okay, so for this one, I've got this side is opposite, this one's adjacent. So for this, I've got 100 sine 30. Okay, I'm just going to zoom in on this so you can see what I'm doing. Okay, so I've got 100 sine 30 there. That makes this side the adjacent, so that force on the bottom there is 100 cos 30. Now, as I said earlier on, where we take positives and negatives, don't worry about positives and negatives when you're doing equilibrium, because obviously that's taken care of by the fact that you're putting one equal to the other. Okay, the negative gives us a direction, but since we're putting all the right ones equal to all the left ones, the positive and negative part doesn't matter anymore. So if I look at this one, this is our opposite side, this is adjacent, so that makes this side 140 sine 45. And this side at the bottom 140 cos 45. And then I've got my force here that is a force of P and an angle of theta. So you've got this side is opposite and this one's adjacent. A little bit more awkward to label, but the opposite side here is just going to be P sine theta, and the adjacent side is going to be P cos theta. So you can see there's a lot going on in that diagram, a lot of different forces acting everywhere. But because it's in equilibrium, we're basically going to resolve in the 2 directions of motion, or lack thereof motion this time. So what we're going to do is, if I resolve in a vertical direction, okay, now because I'm just saying up equals down, I'm not actually saying upwards is positive and downwards is negative. I'm just going to go with everything pulling the object upwards has to equal everything pulling down. So the vertical component of this force was 140 sine 45. I've also got the vertical component of this one, which was 100 sine 30, and that has to equal the vertical component here, which is P sine theta. Okay, now I'm just going to chuck that left hand side into the calculator. 100 sine 45 plus, sorry, that was 140. And then I've got plus 100 sine 30. And I am going to leave it as 50 plus 70 root 2. So I've got one equation. Okay, now it's very common obviously in these to basically end up with 2 sets of equations. One's going to have sine, one's going to have cos, so you can pretty much guess where we're going to go with that. But if we resolve horizontally, I've got the only force pulling to the left is this one, so I've got 140 cos 45 has to equal, and the 2 forces pulling to the right was 100 cos 30 and p cos 30. We want p cos 30 to be the subject of this equation, so p cos 30 has to be equal to 140 cos 45 minus 100 cos 30, which is going to give us 70 root 2 minus 50 root 3. So I've got a second equation. Now that I've got an equation that's in terms of sine and one in terms of cos, okay, why did I write 30? That should say theta. Sorry about that, guys. In which case, because they're sine theta and cos theta, I can turn sine and cos into tan if I do this one divided by this one. P's would obviously cancel out. I'd end up with tan theta equaling all of the sine one divided by the cos one. Okay, and then that means that I can work out theta by just doing tan to the minus 1. So I've got I get an angle theta of 85.2 degrees. Okay, and then all we're going to do with that is then plug that back into one of our equations and solve to find the other number. So I'm just going to use this one. That gives me that p sine of 85.2 has to equal 50 plus 70 root 2. So I'm just going to divide by sine of this. So I get 50 plus 70 root 2, and I'm going to divide it by sine of the answer. I get p equals 149.509 and so on. So two significant figures, I get 150 newtons. Okay, or three significant figures, two significant figures, both came out the same. And that's it. So I've got my force, for my unknown force here, had a force of 150 newtons acting 85.2 degrees below the horizontal. Okay, so that's everything you need for exercise 5A, and I am going to do this as separate videos because that's a lot longer than I anticipated.